Welcome to Ask and Learn.
In this problem, we have a room that is heated by a radiator and the warm air is distributed by a fan. Heat is also lost from the room, and we wish to calculate the time it takes for the air temperature to rise to 20 degrees Celsius. We assume that air is an ideal gas, the kinetic and potential energy changes are negligible, the constant specific heats at room temperature can be used for air, the local atmospheric pressure is 100 kilopascals, and the room is airtight. Now the properties of air is one, its gas constant from our tables is 0.287 kilopascal meter cube per kg Kelvin. The specific heat at room temperature is 0.718 kilojoule per kg Kelvin. So if we take the air in the room to be our system, the system is closed since no mass enters or leaves. So we can write our energy balance equation as E in minus E out is equal to the change in energy of the system, delta E. Now we have heat into the system plus the energy due to the work that the fan does, which is also into the system. So that's Q in plus W fan in minus some heat is lost, so that's minus Q out. And this is responsible for a change in internal energy of the system, delta U. Now we can write delta U as M, the mass of air, times its specific heat capacity, which we'll take at room temperature, MCV average, times the change in temperature, T2 minus T1. Remember, the kinetic and potential energies are zero. Now we can also write this by taking the time derivative of the left-hand side and multiplying it out by delta T. So the rate at which heat enters the room plus the rate at which the fan does work, or the power output of the fan, minus the rate at which heat leaves the room, dq dt, all this multiplied by delta T is equal to the right-hand side. So essentially, by the chain rule, we have the rate of change multiplied by delta T, and that's equal to the right-hand side, which stays the same. So mCV into T2 minus T1. So the first thing we do before using this equation is we find the mass of air. The mass of air, m, we get from its volume. So the first thing we do is actually find the volume of air. So we're given the volume of the room. It's 4 times 5 times 7. And so the volume of the room is 140 cubic meters. So now we can find the mass of air, m, using the equation m is equal to P1 V for a constant volume over R T1. So the initial pressure is atmospheric pressure 100 kilopascals, and the volume we calculated to be 140 cubic meters. And all this is divided by the gas constant of air, R, which we found from our tables to be 0.287 kilopascal meter cube per kg Kelvin, and the initial temperature is 283 Kelvin, 10 degrees Celsius. And so if we do this calculation, we get the mass of air to be 172.4 kg. Now, if we use the CV value at room temperature, and we go back to our energy balance equation, we get the following. So we substitute our values in, and we get 10,000 minus 5,000 over 3,600. So that's the rate of energy transfer, and that's kilojoules per second plus 0.1 kilojoules per second times delta T. So our rates of change of energy in and out of the system is equal to the right-hand side of that equation, which is firstly the mass of air, 172.4 kg times CV, which is 0.718 kilojoule per kg degree Celsius, times a change in temperature of 20 minus 10 degrees Celsius. And so if we rearrange this equation, we can find the time delta T. So we're calculating the time it takes for the air temperature to rise from 10 degrees Celsius to 20 degrees Celsius. And we get delta T to be 831 seconds.